Okay, for this chapter, we're not going to talk a whole lot about it. The book will go into way more detail if you're looking at it, and if you'd like to know more, that's fine. We're only going to cover a very small section of this chapter on this topic we call hybridization. I had to move myself some. I'm trying to get the autofocus in the camera to work. Because you saw my last video where I had to stop for 2 minutes. So hybridization, what is this dealing with? What happens is it turns out when our molecules bond to like form all these shapes, like when we talk about CH4 here and how it's, I'm going to deal something, a shape I like better. Let's talk about BF3. I'm better at drawing things that are in the plane of the board. So BF3, when we talked about this molecule, we said that these were, this isn't, that's fine. This example isn't as good as CH4 actually. But what's important is the shapes this molecule takes doesn't match up with what we might think of the shapes of s and p orbitals. Remember how p orbitals, if you want to make a bond with them, those are those dumbbell shapes, right? Well, if you try to make two dumbbells connect, it seems like they'd be at 90-degree angles to each other. They'd be like these XY angles that would cross into each other. The problem is, you just learned in the last chapter that that's not what these things do. Like this is a 120-degree angle. So the shapes they take, it turns out, are called hybrids. What happens is the orbitals mix together to make new shapes compared to when the atoms are by themselves. So for example, here for BF3, this makes a shape we call sp2. So what's happening there? How in the world did I know this is sp2, and what does this have to do with anything? So anytime you're making these shapes, you're working with a few orbitals. You're working with your s orbital, you're working with up to 3 of your p orbitals, and then you run out of orbitals there, and then finally we have some shapes start to deal with the d orbitals, the next 2. So your hybrids, what happens is you always start with an s orbital. That's where your first electrons go. But then you have to mix them up to make these shapes. So if, for example, you need to mix together 2 sets of electrons, you get an sp orbital. That means this is the shape, the hybridization, for something with 2 electron groups. So this is going to match up with all the stuff from the previous chapter. Electron groups. 2 electron groups is linear, and it's also going to be an sp hybridization. We have 1 s orbital, 1 p orbital. Well, if I want 3, on the other hand, so let's say I want to add another electron group, I got to add another p. That'll be sp2. And that'll be 3 electron groups. So our trigonal planar, this one here, is 1s and 2 p's combined. Well, we can combine another one, sp3, that'll be our 4 electron group shape. So that'll include another p. Things like our CH4, our tetrahedrals. We can keep going. Remember the expanded octets? The expanded octets start to use these d orbitals. That's why they have those different shapes. So for example, we have sp3d. That'll be 5 electron groups. So that will be our trigonal bipyramidal. So something like pf5, for example. And then sf6 as an example would be sp3d2 because it has 6 electron groups. So in terms of learning the hybridizations and where they come up, they are just sp is 2 electron groups. So all your linears have that. sp2 is 3 electron groups, sp3 is 4 electron groups, sp3d is 5 electron groups, sp3d2 is 6 electron groups. Now, I'll be the first to say, your textbook will do an excellent job of showing you pictures of what these things look like. My ability to draw them is non-existent. So please go to your text and look at pictures of these. Or if you really don't like using your text, literally Google pictures of sp, sp2, sp3. That'll do fine. Me trying to draw those orientations I don't think will help you a whole lot. It will just be, what did Dr. Leslie put on the board? I'm now more confused. So check out those pictures. That will help with those. Now, the only other thing we're going to worry about is how these things work and how to think about how these molecules have shapes when we start having double and triple bonds. Specifically, where the electrons go. So it turns out, things like this sp and sp2, you may notice, see, we're combining these orbitals here. But you know that all your molecules could have up to 3 p orbitals in any of its levels, right? You could always have 3 p orbitals because m sub l could be -1, 0, or +1 when L is 1. Remember, L is 1 is your p orbital, means m sub l has 3 values. That's why you have 3 different orbitals. Well, if you only use some of these, the others are available to, those p orbitals, those dumbbell shapes are still around to form bonds. So what we want to know is, when they form a molecule, where the heck do those bonds go? And how does that change their behavior compared to the hybridized orbitals? So, what we're going to deal with is something we call sigma bonds and pi bonds. And so if this seems like a lot, I'll just mention this is the entire chapter, and this is the only parts of the chapter you have to know. So this is a very condensed version. The chapter goes into great detail, so if you want to learn about molecular orbital theory, go there. I love that stuff. I've just learned that it ended up not being worth the time. We had to cut something somewhere, so that's what got cut, was 2/3 of this chapter. So sigma bonds are going to be ones that occur directly between two atoms. So if I'm an atom, and there's another atom across from me, the electrons are going to be shared right between us, which is where you would expect a bond to be probably, right between the two atoms. So in a molecule, like here, BF3, each of these, the electrons occur between the boron and the fluorine. And again, this is somewhere where I definitely recommend looking at pictures. So sigma bonds are going to be those. Now in the other case, sometimes when you have double and triple bonds, the issue becomes, wait, electrons can't be in the exact same place as each other, right? So how do we make a bond? Because a double bond, shouldn't all the electrons be between? Wouldn't they just bump into each other? So what happens, like let's take the example of CO2. Let's do carbon monoxide. So, no, wait, carbon monoxide is really hard to draw on this board. Let's do carbon dioxide. So to do its bonds, what I'm going to do is I'm going to talk about where they happen. So this is a double bond, so we'll have over here. This is two double bonds. So what occurs is the first bond occurs between the carbon and the oxygen. So we've got a bond here and here. I can't draw it. I'm just going to draw circles. They've got fancier shapes. You can go look at them in books. But the general idea is the electrons occur between the two atoms. These are called sigma bonds. Sigma bonds are the ones that occur directly between atoms. Once you have a single bond, though, your double and triple bonds can't go in the same place. So they form something called a pi bond. In a pi bond, you're going to happen either parallel or, so like on top and bottom, so like they'll happen up here and down here, or they'll happen like out here, like if I were to be able to, you can't see my left hand. So I do have a left hand, it's on the other side of the board. So it's like if you had electrons here and here, and then there was a molecule in the middle of it. So we have pi orbital, we've got the p orbitals, which are these dumbbells, and they're going to overlap each other. And that overlap is where our pi bond is. So this is a pi bond. And that same idea can happen here, but it has to like happen into the sideways, which I can't draw. This is why I'm going to say your textbook is your friend. It has pictures of what these things look like. So the way this comes up practically, how do we identify these? So the first thing to note is our sigma bonds are stronger than pi bonds. This is because there's better overlap. They're occurring right between the two atoms. So our sigma bonds are going to be our stronger bonds, whereas our pi bonds are going to be weaker than sigma bonds. They're related to each other. So our sigma bonds are going to be, all single bonds are going to be sigma. So anytime you have a single bond, and I just realized that's not really readable, I'll make sure to say the words. If you have a single bond, it's always sigma. Now if you have a double or triple bond, the first bond is always sigma. Pi bonds, on the other hand, will be additional bonds. So anytime you've got a double or triple bond, after the first bond, all the rest of them are pi bonds. So for example, in CO2 that we just drew earlier, what you could say is, we'll circle a different color, the first one is a sigma bond, and the other two are pi bonds. So this molecule would have 2 sigma and 2 pi bonds. Now, we can do this with other molecules. So if I have carbon monoxide, it has a triple bond in it, and then one lone pair. It's going to have 1 sigma bond, so it'll have 1 sigma and 2 pi bonds. So this is how you'll identify this. Sometimes you'll end up with much more complicated looking molecules, but this is an example of a question type that I think can look really scary, but because of how you calculate them, they're actually pretty easy to see. So imagine we drew this shape here. And so this doesn't look like anything you've seen before here, but, so, 1, 2, 3, yep. So wow, initially this might look like, oh my gosh, how in the world am I going to do this? This looks so much harder. But we're just counting our single and double bonds. So remember, for every double bond, there's 1 sigma and 1 pi. So I can do my pi's first. There's three double bonds, means we have 3 pi bonds. And then if I want to know how many sigma bonds, well, 1, 2, 3, 4. I'm going to start at the bottom. 1, 2, 3, 4, 5, 6, 7, 8. I'm going to circle them as I go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 sigma bonds. Basic math and counting gets very difficult when you're in front of a camera and a board, it turns out. Just like for you, it gets harder when you take a test, I know, where you're like, I knew this thing, but I forgot it. So I circled them so I would keep track. So there are 12 sigma bonds and 3 pi bonds. So asking questions like that can happen when you have molecules that look just impossible for you. You're like, I can't draw a Lewis structure of that. But even for more complex molecules, this part is fairly easy to identify. And so this is actually going to be all we really worry about with hybridization. It's like an extra step on Vesper for us. It is, based on these shapes, it's related to what types of orbitals get combined. And then you'll have to look at some pictures in your text, and we can do some of those, and I think we'll talk about that a bit in our workshop sections as well. So, but for us, this is about as far as we're going to go with hybridization. I will say that this comes back up in organic chemistry. It won't just disappear. And there's a lot more to this question. We have ultra simplified this, and there's definitely some things we're not covering in completion, but this is as much as we can do. If you would like to learn more, especially if you're an upcoming chemist, rather than I'm taking this because, well, I'm a biologist or I want to be a nurse or something, and you made me take this class and I really don't want to learn chemistry. And I understand that. I want to make this as accessible as possible and still useful to you. But if this is something you're like, no, I definitely think I want to be a chemist, I think it's worth going and looking into some more detail. In our text, it does a pretty good job of going into more detail than I just did. And you can get a feel with some of the pictures. And it goes into another thing called molecular orbital theory that I used to teach in this course. And we've moved into some of our other courses now instead that I really think is nice to learn as a freshman. I thought it was helpful to me. So if you have the time and are so inclined, I think that's helpful. At the same time, you can get through your assessment questions if you can count sigma and pi bonds and tell me the hybridization, SP, SP2, SP3, those things. If you can do those 2 things and kind of get an idea of some of these pictures and be able to look at a picture and identify what's a pi bond, what's a sigma bond. So look at examples in your text. I know this is incomplete here. You'll be okay. So with that, I hope this goes okay, and I will see you in class soon. Or if you're just watching me on the internet, I won't see you in class, but still hi, and I hope you're doing well.